Hello, everyone. I hope everyone can listen me. My name is Leonardo Souza. I am assistant teaching professor here at City College for the Carnegie Mellon University. And today I will be the chair of the session, the software testing 6, the name of the session. We have 6 papers to go through, and we already know the drill at this point. Every presenter will have 5 minutes in this first part of the session, so you can present and discuss your work. When we reach the 4 minutes the 4 minutes milestone, I will post a message on chat saying that we have 1 minute left. And after that, we'll go through all the 6 presenters. And the remaining 30 minutes of the session will be for us to ask questions, to discuss the common and difference, all the relations between among all the different work that we're presenting today. And that is pretty much everything that I have for you guys. Do you have any questions before we start? All right, I'll put my chronometer here for every presenter so I can monitor the time, and then you can start with Bokin and his work, algorithmic profiling for real-world complexity problems. So you can share your screen and start your presentation.
Okay. Okay. And everything good?
Yes, go ahead.
Yeah. Okay. See. Hello, everyone. I'm Bo Qin from China Telecom Cloud Computing Corporation. Welcome to my talk. In this talk, I'll present our TSE paper, Algorithmic Profiling for Real-World Complexity Problems. This is joint work with Tengfei Tu, Ziheng Liu, Professor Tingting Yu, and Professor Lin Haisong. Complexity problems are a special type of performance bugs. They are caused by algorithmic inefficiency. Here is an example from MySQL. Function XML parent takes 2 parameters as inputs. The first parameter, items, is an array of XML nodes. A node's level field represents the node's XML nested level. The second parameter is an array index. The function searches the parent of the node, indicated by the second parameter. The loop iterates through items backwardly and searches for the first node, whose level is 1 less than the input node. This piece of code looks innocent. However, there's an outer loop not shown in the figure. The outer loop keeps calling the function using the next sibling of the previous XML node. Thus, the function has n-square complexity in the number of children of a parent node. Developers may think using an implementation in n-square complexity is fine, since an XML node usually does not have too many children. However, during a performance failure run, an XML node has tens of thousands of children, leading to a significant slowdown perceived by the end user. The patch is to add a new local variable in the outer loop to keep track of the current parent, and completely remove the call of function XML parent. Many complexity bugs are like this MySQL bug. They cannot be optimized away by compilers. Fixing them can gain a huge performance improvement. Moreover, complexity bugs widely exist in software. As shown by our empirical study, they cause half of the user-perceived performance issues. Programmers usually rank complexity bugs as high priority in the development. For example, Mozilla developers will immediately try to fix complexity bugs, degrading exponentially. Therefore, it is important to combat complexity bugs. However, fighting complexity bugs is challenging. A good technique needs to satisfy 3 requirements. Firstly, it must provide precise execution complexity for each piece of code. Second, a slowdown caused by a complexity problem. The technique must accurately pinpoint where the root cause is. Third, it cannot incur a large runtime overhead, because it is desired to run the technique in production runs to determine whether a complexity bug causes real performance impact and deserves to be fixed. In our paper, we designed COMAIR that satisfies the 3 requirements and can effectively detect complexity bugs. Here is the infrastructure of a COMAIR in production environment. First, COMAIR takes a program as input and creates multiple program versions. Different program versions have different code constructs instrumented. Second, COMAIR analyzes each program version and conducts code transformation for optimization, approximation, and sampling to reduce runtime overhead. Third, COMAIR analyzes runtime profiles collected by different program versions when they are executed by different end users under different user inputs. Finally, COMAIR computes cost functions for different code constructs based on the profiles, and outputs a ranked list of code constructs in terms of their likelihood of containing performance bugs, and presents the ranked list to the developer. Here are the conclusions. We conduct the first empirical study focused on complexity bugs, where we studied 36 real-world complexity bugs and obtained 3 implications for algorithmic profiling. Then we implement COMAIR, a practical algorithmic profiler which can work under both production run and in-house settings. It provides a novel ranking mechanism to identify root causes with fewer false positives than APROF and OProfile. More importantly, the runtime overhead under production run setting is constantly under 5%, making it practical for production run environment. For more details, please refer to our paper. Thank you.
All right, thank you, Bochin. Now we can move to the second paper. To what extent do deep neural network-based image classification models make unreliable inference?
Can I see my screen?
Yes, you can see it.
Okay, let me start. Hi, everyone. I'm Yun Jiang. I'm a PhD student in University of Waterloo and Hong. So wait a minute. I can always hear the ankle, so I cannot focus speaking. Do you know how to address this issue?
Sorry?
I always hear the ankle from the sound.
Oh, okay. So I will ask everybody else to mute yourself and let just Yongzheng.
Okay. Okay, it's now. Okay, better. Okay, let me restart. I'm in China, PhD student from Hong Kong UST and the University of Waterloo. I'm going to present our work towards extend to DN-based image classifications model. Sorry, I still hear the ankle.
So I think the problem is in your end because everybody else is muted.
Okay.
Are you wearing a microphone? A headphone?
Yeah, I use. Can you hear me?
Yes, we can hear you.
Okay. Now let me try to be focused. I think there's some computer problem in my hand. So our work is published in Integral Software Engineering 2021. It's multi-graduate work by several universities. So as we know, deep neural network is widely used for image classifications. Its accuracy outperforms many old techniques. However, a challenge here is that it's hard to understand how the inference is made by DNNs, specifically the logic of the deep neural network.
Sorry, Yongzheng, I don't think you can hear you.
Okay.
Maybe go back to the headphones.
Okay. I don't know what's the problem here. Test configuration is correct. Hear me now?
Yes, we can hear you.
Okay. So let me start from this slide. So deep neural network is widely used for image classifications. However, a challenge here is that it's hard to understand whether inference is correct or not. Specifically, the logic is encoded in the weight and architecture, which is very hard to interpret and comprehend. This come up with a new question: can we trust the inference made by DNN model? So given this example, here is a play. So DNN models may tell us it is a play. However, the answer is correct, but we have no idea whether the inference is made by the feature of play. So what if this inference actually is made by the feature of sky? So can we still trust the inference if it is majorly based on the feature of sky? So the answer is no. Otherwise, any image with sky will be classified as plane. So in other words, it's possible that the correct decision made by DNNs is based on the unreliable inference process. So in this study, we divide the features in image into two parts. One is object relevant features, which is encoded from the object. Another part is object irrelevant features, which is encoded from background, such as sky, ground. So we also argue that the inference made by DNN models should be majorly based on the object relevant features, such as play, instead of object irrelevant features. So we name this property as object relevance property. Otherwise, if the model does not follow this property, we argue that the inference and the model cannot be trusted because it classifies the image based on specific background instead of the object. So in this study, we propose a testing method to validate whether the object relevant features is validated by the model. So we propose two metamorphic relations. Specifically, the first one, we think that an image mutated by corrupting the feature of the subject object should lead to a different inference result. For the second relations, we argue that an image mutated by preserving the feature of the target object and corrupting other features should lead to a similar inference results. Based on the metaphor relations, we construct the new test and feed them to the DNN models. We check the results, compare whether it violates the metamorphic relations, and if yes, we argue this is an unreliable inference. We manually check the effectiveness of our approach according to 4 models as 2 datasets. The true positive rate is larger than 80%, and the false positive is majorly due to the dataset annotation. We also conduct an empirical study for the latest DNN model. Here is some findings. So first, we find that such unreliable inference is very common in DNN-based image classifiers. We also find that the images with small objects are more likely to be unreliable. We suggest that the developers should pay more attention for such inferences. We also found that unreliable inferences induce bias to model evaluations. For example, removing the unreliable inferences violating MR2, the top accuracy is increased by 8%. The last finding is that the normal training strategy cannot completely resolve this problem. So we hope that more advanced training strategies are needed. There are more details in our paper. That's all my presentations. Thank you.
All right, thank you. We can move to the third paper, Testing Machine Learning System in Industry, an Empirical Study. Xu Wei.
Can you see my screen now?
Yes, we can see it.
Oh, okay. So hello everyone. I'm Shuyue Li from Xi'an Jiaotong University, and I will share one work of my team, which is an empirical study on testing the machine learning systems. So first, I guess most of us are familiar with the machine learning software systems, no matter in research or in our daily lives. In general, these systems have some new properties which do not exist in most traditional software systems. For example, their behaviors can be statistical and determined by data. So we naturally wonder how these properties or these machine learning incorporations affect the software testing process. For example, we usually don't have test oracles, and the test results of machine learning models sometimes cannot be reproduced. But despite these problems, the industry has developed some remarkable machine learning applications which are very successful. So it's natural for us to absorb some inspirations from the industry. And to the best of our knowledge, the testing problem on machine learning systems has not been well studied from this perspective. In this paper, we conducted a study to investigate how practitioners test their machine learning systems, including their major testing activities, their good practices, open challenges, and so on. And our methodology is based on interviews and surveys among the practitioners. So first, we interviewed 7 senior practitioners from different countries. And in these interviews, we carefully investigated their concerns, practices, and challenges on major testing activities. And then we designed a questionnaire and distributed it to practitioners to verify our findings in the interviews. We received responses from various product areas. So with these interviews and the survey, we organized the results of our study by 3 major testing activities, which is test data collection, test execution, and test result analysis. Due to the time limit, I only introduced several interesting findings here. So first, we noticed that most research work on machine learning testing in our community are focused on test case generation for machine learning models. So we wonder how these techniques are adopted in industry, but in our study, none of our interviewees have adopted these techniques proposed in research. And the major reason is that existing techniques are all based on seed inputs and then mutate the seeds to generate more test cases. But for developers, even collecting the seed corpus is expensive. So in other words, the pain point has not been well addressed yet. This is an open question and could be a good research opportunity, I think. And secondly, in machine learning systems, there is entanglement among data, model, and the source code, which makes the testing process less efficient. Although we can test each component individually, they are entangled internally, so any changes on the system could mean to retest all components. Moreover, in our survey, we find that there are different architectures of machine learning systems. For example, the hierarchical system divides a problem into some sub-problems and solves the sub-problems with multiple models. And our respondents also find that testing these kind of systems could be even harder. And finally, we need to conduct test result analysis. And in practice, the quantitative analysis is based on evaluation metrics such as accuracy, recall, and so on. And most respondents in our survey agree that designing the evaluation metrics for machine learning models is a sophisticated task. There is no consensus on which metric is the best because the models are statistical or even uninterpretable, and there are so many properties to test. So we also received many open questions in this part. For example, for a hierarchical system, how to aggregate the metrics on each part to evaluate the whole system. So to conclude, in our study, we find some important implications from the industry for machine learning testing. We hope this work could provide some insights and make the researchers better positioned to help practitioners on machine learning testing. Yeah, that's all. Thank you.
We can move to the next paper. R2Z2 are the authors of this paper here. I don't see the authors, so let's move to the next paper. Fuzzy class specifications. Facundo.
Okay, can you see my screen?
Yes.
Okay, thanks. Well, hi everyone, this is Facundo Molina from University of Rio Cuarto in Argentina, and in this talk I'm going to present fuzzing class specifications, a work developed in collaboration with Marcelo Damorim and Nazareno Aguirre. So to start, let me describe a typical automated analysis scenario. Usually when we want to analyze our programs, we use a program analysis tool that provides us with some feedback on the behavior of our programs. And when we incorporate a specification of the expected behavior of our software, the analysis performed by these tools can be considerably improved, allowing us to catch more bugs or to have better guarantees on the behavior of our programs. But unfortunately, specifications are seldom available, and this situation illustrates the relevance of the Oracle problem, which is the challenge of distinguishing between correct and incorrect software behavior. There are many approaches that one may take to the Oracle problem. One is to try to manually specify the expected behavior using some formalism. Another is to try to analyze the software in order to reveal general software faults, such as unexpected exceptions. And another approach is to try to derive specifications from existing software elements, such as a previous version of the system. Our approach focuses in this last method and in a particular instance of specification inference. We take as input a program and executions of this software, and then using a specification inference tool, we report assertions or specifications that are consistent with observations made in the provided executions. And our goal here is to infer a specification capturing the current program behavior. Several techniques for specification inference have been proposed, in particular the well-known tool DICON, which uses dynamic analysis and a template-based approach in order to infer assertions that belongs to a standard assertion language. DICON has some known limitations. For instance, it typically reports false positives and redundant assertions. And also the assertions that DICON reports are simple arithmetic and logical expressions. In order to overcome these limitations, other techniques have been proposed, in particular GAssert and EvoSpecs. These approaches uses evolutionary computation in order to explore a larger search space. They also use mutation-based techniques in order to report less and stronger assertions. And finally, they incorporate more expressive assertion languages, including further operators. These techniques share some limitations. The most important one is that the assertion languages that they have are difficult to adapt to support further assertions. In this work, we propose a new technique for specification inference called SpecFuzzer. SpecFuzzer is built on top of DICON, and DICON originally takes as input a program and a test suite, and then from a set of candidate assertions, it reports a set of likely invariants that are essentially assertions that are not falsified in the test suites. With the goal of removing the need of manually specifying new assertion, we incorporate in this process an assertion grammar, and then using a grammar-based fuzzer, we're able to produce thousands of candidate assertions that we give as input to DICON. And then by executing DICON, we're able to report many more likely invariants. And then with the goal of only reporting the assertions that are more relevant, we implemented a mutation-based selector that discards the redundant and irrelevant assertions and report the most relevant ones. To evaluate our technique, we took 43 subjects from the literature, and then we incorporated ground truth assertions for each one of these subjects. And then first, we evaluated the effectiveness of grammar-based fuzzing at generating relevant assertions. And in this case, we were able to report more than 20,000 assertions while discovering 61% of the assertions present in the ground truth. Then, in the second phase of our experiments, we incorporated the assertion selector and evaluated the performance of our mutation-based selector. And in this case, we were able to reduce the reported assertions by a 95%, and still discovering 52% of the ground truth assertions. And finally, we compare SpecFuzzer with alternative techniques. And in this case, SpecFuzzer was able to report most of the assertions that also were reported by the alternative techniques. And we were also able to outperform the other techniques in terms of discovered assertions. So to conclude, I would like to highlight some remarks. First, the Oracle problem is a relevant problem in software engineering. Our approach uses grammar-based fuzzing and mutation-based selection to effectively improve dynamic invariant detection. And specification inference can still be improved in terms of scalability, expressiveness, and precision. So thank you very much for listening.
We can move to the last paper in the session, GIF-Droid, Automated Replay of Visual Bug Reports for Android Apps. Sridhar?
Yep. Can you see my screen?
Yes, we can see it.
Okay. Hello, everyone. My name is Sidong from Monash University. I will present our work, GIF-Droid, Automated Replay of Visual Bug Reports for Android Apps. First, I would like to briefly recap the motivation of our work. Bug reports are vital for software maintenance that allow users to inform developers of the problems encountered. However, writing a clear and concise bug report takes time, especially for non-developer or non-tester users who do not have that expertise and are not willing to spend that much effort. A poorly written report will be even poorly interpreted. Compared to write it down with instructions, video-based bug reports lower the bar for documenting the bugs. First, it is easy to record the screen as there are many tools available. Second, video recording can include more detail and context, such as configurations and parameters. Despite the benefits of the video-based bug report, it still requires developers to manually check each frame in the video and repeat it in their environment. We found that bug recording of a large number of frames at very resolution make it difficult for developers to replay them in their settings. And also, as the important information to show users' actions, some recordings may contain touch indicators. However, we found that there are only few recordings enabling the touch indicator, make developers have to guess and try the potential actions to trigger the target page. Therefore, we are motivated to develop an approach to automatically replay the recordings for developers and testers. Our approach consists of three main phases: keyframe location, GUI mapping, and execution trace generation. That is said, given an import bug recording, we first localize a sequence of keyframes and subsequently map them to the existing GUI transition graph to extract the execution trace. Next, I'd like to briefly introduce each phrase. First, for the first phrase, the goal is to identify keyframes, that the states in which GUI are fully rendered. To achieve that, we leverage the image processing techniques to build a similarity score for consecutive frame comparison. And by observing the frame sequence, we annotate the keyframes from the recording if the GUI is in a steady state. That is, the consecutive frames are similar for a relatively long duration. Then, we map each located keyframe to the GUIs in a GUI transition graph. A GUI transition graph is widely used to illustrate the transition across different GUIs triggered by typical elements. To map the keyframes to the states in the graph, it is a well-known image searching task. We adopt feature extraction method to compute the similarity score and map the keyframes to the most similar GUIs. And after mapping all the keyframes, we obtain an index sequence in the graph. Finally, we utilize the index sequence to detect the optimal replayable execution trace. However, we face two challenging problems. One is the previous approach for keyframe location and GUI mapping may not be 100% accurate. And the other one is the recording may start from any states in the application. To overcome the issues, we propose an algorithm to address the defective sequence in paraphrase and complement the missing states between application launch and the first keyframe in the recording. In detail, we first find all the sequence between application launch state to the last index state, and then select the sequence that has the longest common subsequence as the execution trace. In summary, the visual bug recording is training in bug reports due to its easy creation and rich information. To help developers automatically reproduce those bugs, we propose GIFDroid, an image processing approach to convert the recording to the executable trace to trigger the bug in the Android apps. And in the future, we will keep improving our approach for better performance. And that's all for our paper. Thank you very much.
Okay, now that we have 30 minutes left in this session, we can open for discussion. So it was recommended to each one of the authors to read each other paper so we can have a deep discussion. So does anyone have a question right now to one of the presenters? Maybe I can go first. So starting, for example, with Sidong was the last one who presented. So, so Sidong, I was wondering if someone decided to replicate your work, for example, using another operating system like iOS, what would be the major adaptation that you need to do right now in your approach?
I think the first one is you need to obtain the grid transition graph.
Mm-hmm.
So for your own app, and because we are using we are testing in the Android, and there are many tools available to extract the grid transition graph automatically. But in iOS, in the different platform, they do not have that kind of tools to extract this kind of stuff.
Mm-hmm.
So I think it will be the first steps to transfer to another platform.
I see. And when you are doing the investigation, did you investigate different type of bugs that can be generated?
Yes, we test several bugs like crashing and some feature bugs. Yes,
Mm-hmm.
like kind of the general bugs in the GitHub.
I see. Did you notice any specific type of bug that somehow was highlighted in the results? Appear more often, or was harder to identify?
There's one failure for our tools. It's the crash bug, because sometimes the crash doesn't exist in the grid transition graph, so we cannot actually map the keyframes to the states in the graph. Yeah, that's one of the failure case, and yeah, honestly.
I see. Yeah, there are some things that are hard to capture. I understand. Yeah. All right. Thank you.
Thank you.
More questions, everyone?
The question for Sidong. Yeah. So Sidong, I didn't read your paper, so I wonder what tools did you use to construct your UTG, or say GUI transition graph? Is it complete enough for your work?
It's not really complete enough. We use two widely used tools to extract the UTG. One is the Firebase developer from Google, and one is the Droidbot, which is also well known. But I think for your own app, many developers have their own UI transition graph that can be used. Yes, and that may. That should be complete enough. Yeah.
Okay, I see. Thank you.
You can also ask questions in the chat, everyone. Just remember to tag the person, to write the name of the person. Meanwhile, let me ask a question to Facundo. So So, so as you are explaining in your presentation, Facundo, you mentioned about the Oracle problem, which is a challenging problem for the developers. So I was wondering if you want to test, for example, a component that has machine learning, can you apply the spec fuzzer, or do you need to change something in the specification to be able to also apply your approach?
I think yes, but you will have to work in the grammar part, trying to incorporate to the language of the grammar some properties of your interest for the machine learning system, and then yes, having some. I mean, probably you will have to develop some extra component to check those properties when you are using the model in some inputs or something. But yes, the general approach, it may be applied, I think.
I see. Have you thought about which direction that you want to go now with the work?
Yes, probably working more in the part of assertion selection, because it's difficult to retain only the most relevant assertions. That's a problem that we face, and we solve in some way, but there is still some room for improvement there, because that has to do essentially with the precision of these techniques, you know.
Mm-hmm. So when you are presenting, I see. So when you are presenting the result, you put a Venn diagram showing that the spec fuzzer was able to cover more, but there was one area on the, I think, Evo spec that was not able to cover. So what is that?
That were properties more related to quantification properties that in the first instance, the fuzzer is able to produce, but those are properties that, because of some limitations in the DICON infrastructure, we are not able to evaluate inside DICON. So that's the reason why we miss the properties, but those are properties that the fuzzer can produce.
I see. And if I understood correctly, the extension that you are doing on top of DICON, you are not using the genetic algorithm, right? This is the other strategy.
Exactly. Yes.
I see.
We're only using grammar-based fuzzing to generate more properties, and mutation-based selector to select the most relevant ones, let's say.
I see. So when you think about those tools, those strategies that use genetic algorithm, most of them have as the main characteristic the fact that they can explore the search space, right? So when you compare these three techniques, your technique and the other two, regarding performance, so how fast you are able to generate the results. So what can you say about that?
In the first, the first thing that I can say is that the first part of our technique, producing candidate assertions, is really efficient, because we are just fuzzing from the grammar, and that can be done very efficiently. But the problem that we have is in the second step, when we try to select the assertions. That is more expensive because it's based on mutation analysis, and mutation sometimes can be expensive. And regarding the evolutionary techniques, one of them, in particular, GAssert, is more expensive because it uses a co-evolutionary process, so that's more expensive. And the other one, EvoSpecs, is actually more efficient than GAssert, but still, it has it sometimes requires large timeouts, you know, to provide an output.
I see. All right, that makes sense. All right, thank you.
Okay, thank you very much for your question.
More questions, everyone? So there's a question for you, Boquin, on chat. Bochin? Hello, Bochin? Yes. Bochin? I thank you. Okay, while you wait for Bochin, let me ask a question to Xunwei. Xunwei? So in your work, you Can you hear me?
Yes, I can.
Yes. So in your work, you surveyed developers about the testing machine learning, right? And you also mentioned that you have different types of areas. So you have some developers that do it natural language processing, or this speech recognition. Did you notice any difference between these different areas in the results?
Yes, actually we did, and it actually depends more on the type of the task. For example, classification task or ranking task, like those search engines or recommendation systems. Yeah, for this system, for different type of tasks, the testing difficulty or the testing techniques would be very different. For example, for the classification tasks, we can easily evaluate the results because we have those labels, right? We can just compare the model outputs with the labels. But for some ranking system like the search engine, we actually find that the developers, they find it hard to evaluate whether these ranking results are correct, because even human cannot ranking a perfect result, for search engine or something like that. So they may put more, it may take more efforts on testing metric design or testing techniques design in these ranking systems. And also we have actually in many NLP and natural language processing field, there are many structured output generation tasks. For example, the virtual assistants like Siri, something like that. The system need to output or generate a sequence of natural language or something like that. It may be even harder to evaluate these systems because we need to evaluate whether the natural language or the sentences generated by the system is correct or is perfect. It's also a very difficult problem, I think. So in testing is also difficult,
Do you know if they mention in the open-ended question about missing automated support for testing?
I guess actually we find some teams, they designed automated tools for their own systems by themselves. And the major part is about the data management part. And because they have this huge amount of data and they frequently update the data set. So they have to design some automated tools to help them manage, for example, the data versions, the data update process. I think they are very in need of this kind of automated tools.
I see. All right. And in this part of the process, there was other step that was also difficult for them, like in the continuous integration, regression testing.
In our paper, we also included the regression testing because we find many developers mentioned that this is a major problem for them because now for the machine learning models, there is no techniques to select or prioritize the test cases in regression testing. So they have to, every time they conducted the process, the testing process, they have to retest all the test cases in their test data set. It's a huge effort. So, but they cannot abandon any test cases because they are not sure whether it's proper. So
Yeah. All right. Thank you.
Yeah,
okay.
Can I ask a follow-up question?
Yeah, of course.
So after the testing, if some test cases fail, is there any insight from the developer saying how to fix such issues?
Yes.
Yeah.
We actually include this part about bug fixing or bug management in our paper. One of the insights we find is that they hardly fix the bugs one by one. Actually, if they find, for example, an input to the model triggered a bug, they would write a lot of similar inputs. For example, no matter in natural language or in CV, they would generate many similar inputs and figure these similar inputs altogether. Yeah, because the machine learning models can hardly be evaluated by one case, right? It is a statistical thing, so they actually fix the bugs in this way. Yeah.
Okay, thanks.
Yeah, it's okay.
All right. More questions, everyone? Bochin, now that you are back, do you want to answer the question in the chat? Okay, so the answer is there in the chat. All right. More questions, everyone? Maybe a question for Yongjang?
Question is welcome.
So, Yongjang, I was wondering about your work, if you can apply the same strategy in another domain. So, for example, deep neural network is also used to different type of classifications, right? Not only for image. So I wondered if it would make sense to apply a similar investigation in another context, and if so, how can you create that those different sets that you presented? Do you have an idea for that?
Yeah, so actually in our paper, in the discussion, we discussed the generalization of our relationship in NLP object detection, something like this. So in the translation, I think it's easily to, like, if we have sentence, and we can change the subject of the sentence that probably, yeah, use some help from the tokenizer. We can change the subject, we can change the noun, we can change the the word which have some similar meanings. We can do something like that. We also have some discussion on the object detection. I think it's similar to the image classifications. So yeah, that's basically what we did. Yeah.
I see. All right. And for that image classification, did you notice like a specific pattern that was harder to determine the inference was more unreliable for a specific type of image?
Yeah, we found that one kind of image that is easily to be unreliable is the image which the subject is very small. For example, if there is a picture where there is a ping pong ball, which is very small with respect to the whole image. For such image, it's very likely to be unreliable. Another example is some sports activities. I think it's related to the quality of the data set in ImageNet. When they mention the basketball, usually it's a basketball with a lot of players. So it's likely that the model actually learns the players or learns the background instead of the ball, which is usually very small. Yeah.
I see. Yeah, that is interesting.
Yeah.
All right. More questions, everyone?
Hello. I have
Hi.
for you. If the disks are unreliable and the stored image may suffer from bit flips, and will the final training result be affected by this unstable storage? Thank you.
I think basically this is the idea of those samples, especially there are kind of advanced examples named one pixel attack. But this is a little different what we did, what the meaning of unreliable in our paper. But the scenario you mentioned actually is true. Like if the bit flips, it's possible the results from the models will change. So you may search the technique named one pixel attack. Yeah, I think I found some similar results.
Okay. Thank you.
You're welcome.
Shuwei, we have a question for you on chat.
Not really.
So did you see the question?
Oh, let me see.
Did you see the question?
Not really. It's in the chat.
It's in the chat. I can read it for you. So about debugging, what was the most typical debugging task after an issue in a machine learning system is identified? For example, improvement to training data, adaptation to machine learning model or architecture.
Okay. Oh, I see the question now. Yeah. Actually, I think there's we didn't find any typical debugging task for all the machine learning system. As I mentioned, there are so many types of tasks and so many types of different machine learning systems, and they have different complexity. For example, some machine learning systems, they only have one model, but actually most of the systems, they actually have more components. For example, multiple models or a feature extraction part and with multiple models. So their debugging techniques could be very different. But one common thing is that they actually usually when they find a bug, they usually inspect the intermediate results between those components or models one by one. Yeah, it seems not very efficient, but maybe that's what the only way now we can debug a machine learning system, which is very it's hard to we can hardly divide a machine learning system into some in the independent parts, so they can only inspect the intermediate results of a model or of a neuron layers, something like that, one by one. Yeah, and when they fix the bugs, as you mentioned, improvements to training data, adaptation to model architecture, they both, these are actually both are useful ways to fix a model, but not that reliable or rest assured to fix the bugs. So they are actually trying all kinds of changes on data model to finally fix their bugs. Yeah.
All right, thank you. Do you have more questions, everyone? We have a couple of minutes in case you have more questions. All right, so I think you can wrap it up for now. We are missing only 5 minutes, so thank you very much. Oh, do you have a question, Young?
No, I just want to say thank you.
All right, thank you. Thank you, everyone. So, and I see you next time. Thank you for joining the session today.
Thank you.
Thank you.
Take care.